Almost completely. Okay, so what were we doing? We were talking about the Hardy-Littlewood maximal operator, right? And we had just showed that the operator was weak 1, 1, right? And what we wanted to show was that, so we showed that, right, that the size of the set where the maximal operator exceeded some value was controlled by the L1 norm of the function over that value, right? This is the weak 1, 1 condition. And we also mentioned that M was sort of trivially, actually we did it for the uncentered maximal function. We also said that M was trivially bounded on L infinity. Oops, L infinity, and we want to show that in fact M is bounded on LP. At LP, right? So that is that if you have some function that's in LP, then MF, the size of MF, the LP norm of MF is controlled by some constant times the LP norm of F. And so it doesn't change the size uncontrollably. Okay. So the proof of this is something that's called Marcinkiewicz interpolation. Some way of getting so this is for P between 1 and infinity. So we're going to interpolate between the weak 1, 1 condition and the L infinity condition and get the bounds in between. Okay. So proof. What you do is you take your function and then you chop it off. So fix that alpha, and then you say, well, let f1 be wherever the function is bigger than alpha over 2, then just let it be f. Okay, but where it's small, just let it be 0. Okay, so you right, wherever your function is large, right, where your function is bigger than alpha over 2, you take it, but everywhere else you sort of chop it off, right? You chop it off wherever it's small. Okay. Okay. So then, sort of obviously, when you look at the maximal function applied to f, that's certainly smaller than the maximal function applied to f1 plus alpha over 2. Right? And what that gives you is a way of, well, if you look at the set that we're trying to control, right? This set that we're trying to control where this is bigger than alpha, well, if MF is bigger than alpha, then MF1 is bigger than alpha over 2. Right, so this is contained in the set where MF1 is bigger than alpha over 2. Okay. Okay. So then what that gives you is that if we look at the size of this set, well, that's controlled by the size of this set, right? But now we can apply the weak 1. We apply the weak 1, 1 condition to this, and we say, well, this is controlled by C over alpha over 2 times the L1 norm of F1, right? The L1 norm of F1, but the L1 norm of F1 is the integral of F over the set where f is bigger than alpha over 2. Okay. Okay. So So now I'm afraid I have to pull out a fact about integrals, namely that if we're looking at the LP norm of m tilde f, that's actually, so this is going to be the mysterious fact that you can actually write this as an integral of the size of the set where mf is bigger than alpha times alpha to the p minus 1 d alpha. Okay, so I'm sorry. This is just gonna. This thing here is called the. This thing here is called the distribution function. Yeah, and I don't know how to explain this. I don't know how to explain this. Yeah, I'm sorry. Just take it as a fact. Okay. Okay. So. I mean, you can think of it like if p is equal to 1, we're trying to find the integral. We're trying to find the integral of just this function, right? And that turns out to be the integral, the sum of the sizes of the sets where mf is bigger than alpha. Okay, so you're like you're looking as alpha goes from 0 to infinity. As alpha goes from 0 to infinity, you're looking at the sets where you're bigger than alpha, right? And you're saying you're taking the sizes of these sets, and then I don't know. That's I don't know if that helps you. But, okay, so okay, so just to, I'm not sure if I can get you back in. I don't think I can get you back in, but don't worry, we'll finish this and we're going to move on to something different. So, okay. So fact, right? Now, now this thing, right? This thing we've just established control for over there, right? So this gives us p integral over alpha from 0 to infinity times 2c over alpha integral, the L1 norm, but over the space where f is bigger than alpha over 2, alpha to the p minus 1 d alpha. Right. So now we change the order of integration. We get the integral dx from hold on a second. So on the inside, we get the integral over d alpha as alpha ranges from 0 to absolute value of f, alpha to the p minus 2. Okay, and then we're left with f dx on the outside. So just switching the order of integration. Okay, but what does that give you? That gives you, this is going to be 2 absolute value of f to the p minus 1 over p minus 1, right? We get cp integral over Rn, cp this, times the absolute value of f dx. Right? So just integrating this guy on the inside here. Well, what's that? That is, we have this, we pull out all these constants, 2 to the p minus 1, cp over p minus 1, and then we get f to the p, integral of f to the p, right? Which is some constant times the LP norm LP norm P. Right? So what we get that the LP norm of this uncentered maximal function is controlled by some constant times the LP norm of the actual function. So we get the LP boundedness. Okay. So this is the trick of so-called Marcinkiewicz interpolation. Basically, just chop the function at that particular height. Okay. Okay. So that gives us the LP boundedness of the maximal function that we promised. Okay. So now, let's see. So now we're going to switch over to. So you kind of come at a good time because we're switching topics. So now we're going to switch over to the singular integrals and see how the control of the maximal function plays into the boundedness of the singular integral operators. Yeah. So don't worry, just trust that we have the boundedness of the maximal operator. Okay, so this is going to rely on a couple of things. Now we're switching over to singular integrals. Okay, and so we're going to use a theorem called the Whitney decomposition. So let me give the original form of the Whitney decomposition, and then I'll give the sort of generalized form. So we're going to be doing the generalized. We're going to be doing the generalized theorem, but just to give you some sense. So here's the idea. So you have F in Rn, a non-empty closed set. And you have FC, the complement. Okay, I'm not going to prove this, but then one can cover FC with cubes, sides parallel to the axes, QK, such that the interiors are disjoint, so the interiors of the cubes are disjoint, and two, the side lengths of the cubes are, basically proportional to the distance of the cube from the original set. Okay, so it's something like this, right? Like you have F and you have F complement, and then you can cover F with cubes where the size of the cube basically is dependent on how far it is to the edge. So the cubes closer to the edge are smaller. The cubes farther away from the edge are bigger. Okay. Okay. So that's the original Whitney decomposition. There's a variant of it, so it's sort of generalized Whitney decomposition, which says the following. So again, given F closed and non-empty, then there exists a collection of balls, P sub k. So there exists a collection of balls. So I should say, let me say it this way. There exists constants, C star bigger than 1 and C double star bigger than C star. Yeah, this is, sorry, I said it backwards. There exist these constants such that given any closed non-empty F, there exist balls B sub k such that when the BK are pairwise disjoint, pairwise disjoint, 2, the union of the BK stars is F complement. Okay. And 3, BK double star intersect F is non-empty. BK double star intersects, so the doubly expanded ball intersects F. Okay, this last condition is basically like this side lengths condition, right? You can expand it by a finite constant and then hit the set. Right. Right. So again, right. Here's your F complement. Right. You've got these balls. The balls are pairwise disjoint. The expanded balls, the union of the expanded balls covers FC, and then if you expand it one more time, then you hit the original set. Okay. Okay. And one can construct from the BK these sets QK such that the QK are disjoint. The QK sit between B and B star, and the union of the QK equals F complement. Okay, and these guys are sort of like the analog of the cubes in the original Whitney decomposition. Okay, so, okay. Okay, so, okay, so we've got this Whitney decomposition, and we're going to use that to get the so-called Calderón-Zygmund decomposition. Calderón-Zygmund decomposition. Right. So yeah. So the field of math that I did, that I was working in was so-called Calderón-Zygmund harmonic analysis. Zygmund, if you want a family tree, Zygmund is like the father, and then there are students of Zygmund's, Calderon, Stein, Pfefferman is, the two Pfeffermans are both students of Stein. Let me just tell one kind of cool story. Some of you may have heard this already, about how Calderon met Zygmund. So apparently in those days, Zygmund would, I think, for some reason, Argentina liked to invite mathematicians to lecture lecture over, and so Zygmund was invited to give lectures there, and he was lecturing on his book on Fourier series, and he saw, while he was giving the proof, he was giving a proof, and he noticed that there was one man in the audience who kept on like scowling, like grimacing and making faces, and he said, "What's wrong?" And the man said, "Professor Zygmund, that is not the proof in your book. The proof in your book was much more succinct, and and he said, no, I wrote my book. I know what my book says. This is the proof in my book." And the young man was like, no, that is not the proof in your book. Oh. So and eventually what Zygmund realized was that this man was of course Calderón, and he realized that Calderón did not actually read the book. did not read the book in the normal sense. What he would do was read the first line of the proof, and then he would try to construct the rest of the proof on his own. And so he had come up with some alternate proof that he thought was in the book. And so Zygmund, like he had come up with some much more clever proof than the proof that was actually in the book. So Zygmund invited him to come to Chicago and be a graduate student, and then Calderón got his PhD in 1 year and went on to to work with Zygmund and create this field of harmonic analysis. I met him one time. There was like a 75th birthday celebration for him at University of Chicago. And he was originally an electrical, before he, I'm not sure why he was in this class, but he was originally an electrical engineer. He actually stood up and gave some questions that were kind of related to electrical engineering.
He got his PhD in 1 year.
Yeah. So I mean, it's even more amazing than that. He published like 3 major papers in that year, and then that was basically his dissertation, and then he got out. So yeah. I think there was another guy I've heard of that finished his PhD in 1 year, and that was this guy named Shin Mochizuki. He's the guy, I may have mentioned this story before, the guy who would turn in his homeworks and just write, "This is trivial" on them. Have I told this story?
Yeah.
Okay, yeah. So
Isn't he the guy who has like the intermular?
Yes.
Interuniversal dicmular?
That's the guy. That's the guy. The ABC conjecture. Yeah. So there's some sort of like 500 page proof of this conjecture that he's put out, and like nobody can understand it. Okay. Too many stories. Let's get back to this. Okay. So how should we do this? Okay, I'm gonna sketch this part out so we can get to the cool stuff after. Okay, Calderón-Zygmund decomposition. You have a function in L1. You fix a constant. Okay. Then you can break. One can decompose f as the sum of 2 functions, g plus b. And generally, it's good, and this is the good part, and this is the bad part. That's what g and b stand for. Where 1, the good part, is bounded by c times alpha almost everywhere, except that it's accepting on a set of measure 0. 2, the bad part, how should I get this? Okay. B is actually a sum of other functions, bk, where this happens, and there exists a collection of balls bk star, yeah, which are the balls from the generalized Whitney decomposition, the expanded balls from the generalized Whitney decomposition, such that when if you look at the integral of the bk, it's controlled by when the support of the bk, each bk is supported in one of those expanded balls. 2, the integral of bk is controlled by C alpha times the size of bk star. Okay, so this is some sort of like average value condition, right? It tells you that the and 3, the integral of bk without the absolute values is 0, so cancellation. Okay, so this is, I don't know, you can either call this like an L1 condition or something. Okay, and sorry, there should be, sorry, I've misnumbered them. This is 1, this is 2, and 3 is that the sum of the bk stars, the size of the bk stars is controlled by C over alpha times the L1 norm of F. Okay. So I'm not going to prove these things, but I am going to sketch out how you get the decomposition. Okay. So here's the construction. Okay. So what you do is you say you let E sub alpha be the set where the maximal function is large. Okay. And then you apply the Whitney, generalized Whitney decomposition. Okay. So you get your BKs, your QKs, your BK stars and BK double stars. So you get these guys such that, as before, the QKs lie between BKs and the BK stars. The union of the QK equals E alpha, equals that set. And the QKs are disjoint. Okay, and then the decomposition is goes as follows. So you define G, the good part, as F whenever X is not in the place where the maximal function is large. So it's F where the maximal function is smaller than alpha. So. Okay. And then, so, remember, E sub alpha we've expressed as this union of fake cubes. So if you are in E alpha, then you lie in some cube. Right? On the cubes, you define G as the average of F over the cube. So you define it equal to F, where the maximal function is small. When the maximal function is large, you define it as the average over that cube. So then let bk be sort of obviously it's going to be defined on the cube, and the value is going to be f minus the average. So you take f, you subtract off the average on that cube, and it's only defined on the cube. And of course, you know the integral is 0. It's got cancellation, obviously. So yeah. So then f is equal to g plus summation bk, and this thing is fb. Okay. Well, I got 17 minutes. Let's see what we can do. Yeah.
So the g is trying to be small enough everywhere, right? Because we have a condition on its modulus.
Mhm.
So why, say f is big somewhere, right? So in one of the qk's, why is taking an average making it any smaller? Why can't f be big on the whole qk?
Well, the thing is that, look, hold on a second. Right. Yeah, the thing is that it's a good question. The thing is that remember that if you expand these guys just by a constant, then you're going to hit the complement, right? Which means that if we take the integral, if we take the average over the expanded ball, then the average has to be smaller than alpha. The average over the expanded ball is going to be smaller than alpha.
Why?
Because
you're saying if you expand them, then we hit the EA where it's
we're going to hit
something that's not in E alpha. So.
Yeah, something that's not in E alpha. In other words, where the maximal function is small. So the average over the expanded ball is going to be small.
Oh, because the maximal function is counting. Yeah.
Right.
I see. Okay, but this is not the expanded version.
Right, but it's controlled by a constant times the expanded version.
I see.
Yeah, and that constant is fixed. So, right, the thing is that you can expand. I erased it, but you expand it by if there's this fixed constant, you can expand it, and then that fixed constant, you're just going to get this thing times.
Right.
You're going to get c, that constant times alpha.
I see. Because that thing is not bounded by alpha, but we have a constant to play with. Yeah.
Yes. Exactly.
Okay. Cool. Thank you.
Yeah. Good. Yeah. Okay. Let's see what we can do. I'm not. I at this point I regret telling stories. Okay. Okay. So singular integral operator. Okay. So the operator is going to be defined like this. I'm going to be a little bit sketchy here, but the operator is defined by integrating the function against a kernel. Okay. So you've got some sort of kernel. It could be like a convolution operator. You're integrating your function against some kernel. So k is singular. That is, it blows up where near x equals y. And so, so this requires that you do it, you consider this as some sort of limiting thing, or in the sense of distributions. So we assume, so if there exists a constant such that TFQ is bounded by AFQ. So if T is bounded on LQ, okay, if T is bounded on LQ, and 2, there exists a measurable function K such that this is true under I'm just going to put that in quotes, such that this is true, and for some c bigger than 1, the integral of kxy minus kxy bar dx is smaller than some constant a, when for y bar in b by delta, where you integrate over the complement of an expanded ball. Okay, so right, so you've got some ball, of radius delta about y, and then you're integrating on the complement of the expanded ball. You have some sort of expanded ball, and you're integrating this difference on the complement. Okay.
What is y bar?
Y bar is just some point. Y bar is any point fixed inside there. So you fix for fixed y bar inside there. For any you fix y bar inside there, and you take the difference between you take the difference between the values of k. Sorry, I'm saying this a little bit wrong. You integrate over x. Sorry, you integrate over x as x ranges over the complement. Yeah. Okay. So so.
Is this saying that as x gets really big, then those two values have to become very close together, or like
No.
in general? Oh.
No, it's just like whenever you have so y is also fixed, right? So whenever you have a y and then a y bar that's close by, and you integrate over the complement of the expanded ball you integrate x over the expanded ball around y, then that thing is controlled. Okay. This thing. Okay. So under and there's a couple more technical assumptions, but then T is bounded in LP, on LP. I.e. TFP is controlled by then for all p between 1 and q, t is bounded on LP. Okay. And what can I show you? So the proof kind of follows the proof of the maximal theorem. You get first you get weak 1, 1 for t. You already have the strong LQ bound. Okay, and then you interpolate between 1, 1 and q, and you get the p's between them. Okay, so the main work is this one, is this thing, to get the weak 1, 1 bound for t. Okay, so you want to show that the place where t exceeds alpha is controlled by some constant over alpha times the L1 norm of f. Okay, and notice that it's okay for us to stick in a constant here because that constant will just wash out here. So we can play with, we have a sort of leeway to play with this constant. Okay, so and the thing to do is you say, well, do the Calderón-Zygmund decomposition at height C alpha. Right, that will split your function into the good part and the not so bad part. So you get f equals g plus d plus b. And then you say, well, look, f is g plus b. So so it suffices to show that we can do this in parts, right? If we look where, right, if this is bigger than C alpha, well, that tells you that one of these guys must be bigger than C alpha over 2, right? Maybe that's not completely obvious, but it's true. Okay, so one of these guys must be bigger than C alpha over 2. So it suffices to show that we have the weak oneness for each of these parts. Okay, so we do it for each of these parts. Okay, so at least let me show the good part. So for the good part, so you split Rn into the expanded balls and their complement. Okay, and then you look at, consider the integral of g to the q over the union of the balls. Okay. Remember that g was bounded by C alpha, so we can just pull that C alpha to the q out, right? And then then all we have is just the measure of the ball of the domain, right? That in turn is controlled by the sum of the areas of those guys, of course. But remember that is, each of those things is controlled by the each of those things is controlled by the L1 norm over alpha. Right. That was part of that was part of the construction that was part of the Calderón-Zygmund lemma, decomposition. Okay, so then okay. On the other part, on the complement, well, on the complement, that's where G equals F, right? That's where G equals F. And so this part is easy. You say, well, look, this thing, the integral over the complement, each of the G's, remember, is smaller than C alpha. So we pull out Q minus one of them. Okay, we pull out Q minus one of them, and we're left with F. Right? We're left with F, but that is right. That's exactly what we. That's well, not exactly what we wanted, but. We get, so we get C alpha Q minus 1, the L1 times the L1 norm of F. Okay, so that's easy. So now, now putting that together, if we look at the size of the set where we exceed C prime alpha over 2, well, that's going to be by Chebyshev's inequality. That's controlled by C prime alpha over 2 to the minus Q times TG times that. Sorry, that may not be completely evident, but it's basically the same argument we did last time that we called Chebyshev's inequality. Okay. Okay. And then from here, you use the LQ boundedness, right? So this is controlled by some constant, alpha to the negative Q, G Q Q. Okay. So this is the LQ boundedness. Right. And then, right, we have, right, this is part of the QQ norm, right? The LQ norm to the qth power, and this is also, right? So you just sum those two things together, and you end up with you know, A prime. Right, C alpha to the Q minus 1 times F1 over alpha to the Q. Right. In other words, some constant times F1 over alpha. Okay, and then, yeah, so, yeah, and then, sorry, I guess I'm not gonna finish. Yeah, so maybe I'll try and record later the second half of this, and so you guys can see. So this is actually the good part, where you can use the where you can use the LQ boundedness directly on the good part. For the other part, you have to use the cancellation. Remember those BKs all have this cancellation condition, and what that allows you to do is sneak in a constant. sneak in a constant, so you'll be doing some sort of integral, right, against f, against b. But the fact that these guys have cancellation allows you to sneak in a constant, right? Just like we've sneaked in the constants before. The same trick as before. That trick allows us to apply the condition, right? That condition that we had. So then there'll be some sort of like changing the order of integration, and then you can apply that condition that we had down here, the condition on the kernel, which gives you the bound, and then that does it for you. Okay, so yeah, breaking the function up into two parts, one of which is the easy part, and then the other part you game so that it's made up of things that have cancellation is really the heart of a lot of this stuff.